All right, so for this one, we're going to try and figure out the volume of the solid that is above this cone and below this, whatever this is. So maybe you can recognize that right off the bat as a sphere, but I don't know if it's necessarily obvious. So the first thing I'd probably do is get to work on this equation and go, okay, so what the heck are we got going on here? So x squared plus y squared plus z squared minus z is equal to 0. But if I add a fourth onto each side, then I can complete the square, and it's x squared plus y squared plus z minus 1/2 squared equals 1/2 squared. So this is a sphere of radius 1/2 centered at 0, 0, 1/2. So it is just sitting on top of the origin like this, and that's the center at 1/2, and then like up here at the top where it pokes out, whoops, let's make that blue. This is going to be z equals 1 up here at the top. Okay, and so then it says above some cone, and the cone is just that guy, right? So looking at these, I can see that the place that they intersect is actually going to be right around that mid-latitude right there. So our region, as seen from the side, looks like this. There we go. So now it's important that it's not the case that this is the radius of the sphere. That would be a much different shape. We've got actually a full half sphere sitting up on top of that cone. Okay, so let's see. So this looks like maybe a good candidate for cylindrical coordinates. So I might start in on that. Turns out it's actually not a good candidate for cylindrical coordinates, but we'll see that soon enough. So let's see. So if I were going to set this up doing a dz integration first, then I'd be looking at going from bottom to top through this solid, like so, right? And so I would be going from z equals r up to z equals, and then I'm gonna come back to this equation here and say, oh, I need a z equals equation for that guy. So what do I have? So this first part here, that's an r squared. So I have z minus 1/2 squared equals 1/4 minus r squared. And then I can take the square root over there. And so then I have z is equal to 1/2 plus square root of 1/4 minus r squared. Hooyah! So things just got ugly in a hurry. So that's our upper bound of integration. R, and this is dz. And so then let's see. So yeah, so we're doing cylindrical shells right now about the z-axis. And then let's see. So R is then going, so I look at these and I say, okay, so where's my first r? Well, this thing contains the z-axis, so it's going to start at r equals 0, and it's going to go outward to, let's see, my last slice was like out here, and so that's at r equals 1/2. So we go up to 1/2, from 0 to 1/2, and then that's going to be, so that's our dr. Theta is going to go from 0 to 2 pi. Okay, so I look at that and I go, oh, ugly. Do not want to deal with. Okay, so let's try doing that again. It's getting worse every time I draw it. And now this time let's think about doing radial integration first. So that means I'm going from axis out to surface, I'm going out to that cone, and to, oh no, now I'm going out to the sphere. Okay, so we're going to have to split it here and do something different. So this is actually a non-elementary region for doing dr first. So let's see, so r dr dz if we set it up this way. Well, we've got this bottom portion here. So this is where z goes from 0 to 1/2. So this would be from 0 to 1/2, 0 to 2 pi for my theta. And now I got to figure out, okay, so what am I going to do about this r situation? And so we're going from the axis out to the line z equals r. So that would be z. Okay, so that's not too bad. But then that, keep in mind, is only for the bottom portion here. And we still have to do the top portion out here. So let's see. So this is going to be now 0 to 2 pi because everything is. And then this is the part where we go from z equals 1/2 up to z equals 1. So we've got 1/2 to 1. And then we need to figure out, okay, so what is the r doing here? Well, now we're going to need to go back to this equation, but solve it for r. So we have z minus 1/2 is equal to 1/4 minus r squared. Like that. Okay. Or actually, no, here, hold on. I'm going to put it over on the other side like this. There we go. So then r is 1/4 minus quantity the business, all in a square root. Yowzers! Okay, so at this point you should be really convinced that this is not the right way to set this up if you want to have a hope in Hades of trying to integrate it. Well, I don't know. It's maybe it's quite possible, but it looks ugly, and I'm easily frightened. So we'll just go from there. R, then this is dr, dz, d theta. Oh, forgot theta. There's a theta. Okay. Okay. So there we've got a couple options to play with, and they're not looking especially nice. So now I'm going to do the last one. Wow. It really is getting worse every single time I do it. Okay, let's see. Boom. Bam. Okay, that was beautiful. I'm going to go with that one. Okay, so now if we do this in spherical, we're going to be going from the bottom to the top. So the radius is going to be going a distance of 1 in that direction, but the distance is going to shrink down until by the time we're going this direction, it's only going like, what is that, root 2 times, root 2 over 2. So let's see. So now I'm going to go, I need to figure out actually what this bounding curve is in terms of rho. Okay, so now I go back and I grab this original equation, and I've got x squared plus y squared plus z squared equals z. Or for spherical, this is rho squared equals, and then z looks like rho cosine phi. And so I've got rho equals cosine phi. Okay, so this is going now from, this contains the origin, so we start at 0. So we go from 0 up to cosine phi, and then we're doing volume, so it's just rho squared sine phi. That's our d rho. And then d phi, so now we need to figure out, okay, so we start going straight up at phi equals 0, and then we pass down through the arc until we get to this one here, which is phi equals pi over 4. So we go 0, pi over 4. And then the last one, of course, is our good old spin it by 2 pi. Okay, and that one looks the most palatable to me to do the integration. So let's see. We can fubinate, and so this is going to be 0 to 2 pi d theta. and then rho. Oh, well, we've got we've got our guy up here in the upper bound, so it's not going to be a rectangle. I better start integrating. So let's see. So this is going to be. So we integrate rho first, and we'll have, let's see, so 0 pi over 4. We've got rho cubed over 3 evaluated from 0 to cosine phi d phi. And so that'll give me a 2 pi over 3, pulling that 3 out front. And then I've got, oh, and I forgot part of my Jacobian got left behind. Let me patch that in there real quick. Sine phi. So then I'm going to have integral 0 to pi over 4 cosine cubed phi sine phi d phi. And now, aren't you glad that I did not forget that Jacobian? Because this right here is going to be my du when I put u equal to cosine phi. And then I guess actually that's minus du. So let's see. Doing that integral, I get minus 2 pi over 3 integral u cubed du. And so that's going to be minus 2 pi over 3 times, and then I'll have 1/4, and then I'll have cosine to the 4th evaluated from 0 to pi over 4. So that's minus pi over 6 now. Okay. And then we're going to have 1 over root 2 to the 4th minus 1. And so square it and you get 1/2, and then square that and you get 1/4. So we're looking at 1/4 minus 1. So we've got pi over 6 times 3/4. And 3's cancel, and we've got pi over 8 for the money.